Hello, this is Yasmin SarcheshmehPour, and in this video, I'm going to present my master's thesis on application of reinforcement learning in electrical machine design. And this project has been done with the collaboration of ABB and the Aalto University. Here is the agenda that first of all, we are going through the introduction and the research goals. Then we are going to have some background information from electrical machine design and reinforcement learning. Then we are going to the reward function section, which is the main contribution of this thesis. And finally, we are going to have the results and the conclusion. Electrical machines are devices that convert electrical energy into mechanical energy or vice versa. They are really important because they utilize about 50% of the worldwide energy usage. In big corporations, there is a need to have a really fast method to design the electrical machines because there are thousands of motors that they are manufactured daily, and each of them should meet some specific customer requirements. Traditional methods are computationally expensive, and they have some problems with finding a global optimum. So there is a need for methods to automate the induction motor design process. The research questions of this thesis are that how can we use RL to find the optimal machine designs? The second question is that how can we use the performance metrics and the cost functions to design a proper reward function? And the final question is that how does this proposed method work compared to existing traditional methods in terms of efficiency and design quality? There has been some works that have been done in this area, but most of them, they have been using genetic algorithms, and there has also been one work which has used a reinforcement learning and evolutionary optimization method to create a linear induction motor. However, these methods have some problems that some of them are time consuming and have tendency to overfit to the training data, and the reinforcement learning work with the evolutionary optimization, it also has the problem that it's not a universal solution. There have also been some works that explore the application of machine learning techniques in electrical machine condition monitoring, but there has not been any work related to designing the electrical machines. Electrical machine design is a parameter optimization problem in which the objective function corresponds to the mass of the motor, and we have the design variables in this work. They are a length, coil turns, and rotor tip height of the motor. Additionally, we have the user specific and manufacturing requirements that are formulated as equality and inequality constraints. Usually, engineers select a base machine that is very close to the user-specific requirements and manufacturing constraints. Then they either manually or deterministically, they adjust some important design parameters, and finally, they will do some further optimizations to fine-tune the design. Unfortunately, this process is time-consuming and can affect the sales negotiation. In order to be able to use reinforcement learning for designing electrical machines, we need to have a simulation environment in which the reinforcement learning agent can interact with. So for designing the electrical machine design game, we have some performance metrics such as rotor to tip height, air gap flux density, starting current, starting torque, and stator temperature rise. And based on these performance values, we are defining some performance flags in which the value of each flag could be either 1, 0, or -1. If the corresponding performance value of the flag meets the user-specific requirements and the manufacturing constraints, the flag value is 0, otherwise it's 1 or -1. Therefore, a machine design can be considered as feasible if and only if its flags are equal to 0. So at each time step, we assess the performance flags, and depending on their values, we decide to adjust a design parameter. Then we will end up at a new state, and the new state has the new performance flags, and we continue this process until we achieve to the final design. Designing electrical machine is challenging because it's a multi-objective optimization. It has high-dimensional design space. The simulation is time-consuming and costly, and we have access to the limited data and expert knowledge. Additionally, designing electrical machines requires balancing different factors, and there are a lot of trade-offs among these factors. For example, here we have the design parameters, number of coil turns, to tip height and length of the motor, and we have the performance metrics here. So you can see how increasing each of the design parameter affects the performance value. And there are some interconnections between these performance values, and changing each design parameter doesn't have the same effect in each of the performance values. So reinforcement learning is the method that we are using to automate the design of electrical machines. Basically, reinforcement learning has 4 key elements, which is the environment, that is the game in which the agent is interacting with. It has a state, action, reward, and also the policy. In our simplified problem, actions are decreasing or increasing each of the design parameters, and the states are flag values aligned with the previous action. In this work, we are using Proximal Policy Optimization as the reinforcement learning method, and the process of designing electrical machine design using reinforcement learning starts with defining design parameters, create the simulation environment, define reward function, train the reinforcement learning agent, and evaluate the optimized design. So far, we have defined the design parameters and the simulation environment, and then we need to define the reward function, which is the main contribution of this thesis. In this work, we have proposed 3 different reward functions. We are going to start with the simple reward function, in which we are not using any human expert engineering knowledge. As I mentioned, a feasible machine design is the one in which all the performance flags are 0. Therefore, the simplest way to design the reward function is to consider the number of 0 flags. Therefore, in this simple reward function, we have flags reward function in which we are calculating the difference between the current 0 flags and the previous 0 flags. This flags reward function has some properties of a good reward function, and it does not have some of them. For example, it's aligned with the task objective, easy to compute, but it's not consistent with the goal. It does not encourage exploration, and it's not general enough. Therefore, we need to add some properties to this reward function in order to make it better. For example, here is also a simple failure case that the agent wasn't able to find a solution only based on this flags reward function. So one component that we need to add to the reward function is the goal reward. It will add the consistency with the goal to the reward function properties. In it works in a way that we are giving the agent a huge reward if the agent wins the game, and we give it a huge penalty if the agent loses the game. Although this reward function is good, but there's a problem that the agent will stuck in repetitive loops, and we need to somehow solve this problem. In order to solve this problem, we are adding some penalty to the reward function if the agent sees a state that already has been seen during the training. So the final reward function would be like this. We have the flag reward function, goal reward function, and also the visiting penalty. This reward function has almost all the properties of a good reward function. However, it cannot be generalized. Therefore, we need to design another reward function which has the engineering knowledge in it. So the second reward function is the human expert knowledge-based reward function, in which we are considering the value for each performance metric. Therefore, this performance reward function consists of the individual rewards for each performance value, and there are some priorities among these performance values in the electrical engineering concepts. So we are considering those priorities in the performance reward function as well, and the final performance reward function looks like this, in which the rotor to tip height flag has the highest priority. In addition to the performance values, we also have the relative starting current requirement, in which in some of the designs we have a target relative starting current requirement that limits the nominal starting current of the induction machine. Therefore, we are adding reward function related to this relative starting current requirement, and the final human expert knowledge based reward function looks like this, that it has the same goal reward as the previous reward function and the flags reward. Additionally, it has the same visiting penalty, and the difference is that we are adding this performance reward function along with the relative starting current reward function. So this reward function has all the properties of a good reward function, that it's aligned with the task objective, easy to compute, consistent with the goal. It encourages exploration, and it also has a good generalization. However, it has the engineering knowledge, and it would be really good if we can also have another reward function in which there is no engineering knowledge injected. So the final reward function is the distance reward function, in which there is no engineering knowledge injected. In the distance reward function, we have a training set, and there is a database that contains the goal states of the training machine. So in each game, we have the goal state of that game, and at each time step, we are at the current step. The design reward function is designed in a way that at each time step we are calculating the distance of the current step to the goal state, as well as calculating the distance of the previous state to the goal state. And then if we moved closer to the goal, then we are giving the agent a positive reward. Otherwise, if we went far from the goal, we are giving the agent a negative penalty. For the results, we have 5 different electrical seat machines with different properties of shaft height, number of poles, nominal power, and nominal voltage. And for each of these electrical seat machines, we have some power multipliers, voltage multipliers, and different target ISPUs that we are able to generate more training electrical machines based on these 5 seeds. So here for the simple reward function, we have started with only 1 seed, so we train the agent only in 1 case. Here is the result for that case. So the blue point is the starting point and the red point is the target point. The yellow path shows the reference solution, in which is the traditional design method, and the green line shows the reinforcement learning path. Then we try to make the game more complex, so we have decided to train the agent with 30 different variations of the seed machines, and the agent was able to find the solution for these 30 different seed machines. So we decided to scale the training machines to about 100, and the agent was still able to find the solution. In all of these 3 models, the state consists of the flag values, previous action, along with the success indicator, which indicates if the action was successful or not. However, if we wanted to scale training set to more than 100 cases, this reward function was not able to find the solution for all the cases. So we have moved to the human expert knowledge-based reward function, and we started with 122 cases. And the agent was able to find a solution for all of the cases, but then when we wanted to scale it to about 400 cases, with the previous state definition, the agent was not able to find a solution for all the cases, so we had to come up with a new definition for the observation space. So the complex observation space is this: we have added the performance values, some of the performance values, to the state space, so that the agent have access to the plain values in order to be able to decide better. Here are examples for the failed cases for the simple observation space for the human expert knowledge-based reward function. As you can see, adding these performance values to the observation space, it decreased the number of needed training steps. And also here, PPO2 reference steps means that how many reinforcement learning steps did we did it take to find the solution for all the 375 cases compared to the total reference steps. And the final, we have the distance reward function, in which we have trained the agent for a total number of 650 cases. As you can see, the distance reward function has almost the same number of steps as the human expert knowledge reward function. However, it has more training steps, which means that for the human reward function, we injected the knowledge, so it makes sense for it to have less number of steps. Additionally, we have splitted the training set to the test and train sets, and we selected randomly 20% of the electrical machine games into the test set, and you can see that this reward function was able to be generalized and find the solution even for the unseen cases. So this reinforcement learning based design method enhances the process and outperform the traditional methods by reducing the optimization steps. And the novel distance reward function makes reinforcement learning easier to use and more flexible by reducing the need for specialized knowledge. For the future work, we need to investigate alternative new reinforcement algorithms, as well as assess the scalability of larger and complex machines. Here is also the answer to the research questions. Thank you for your attention. If you had any questions, you can contact me with this email, and have a nice rest of the day.